Wow. Yeah. They're my favorite GR sources. I'm going to use his metric. I like something he has, and then this is just always cute. It's just Dan Gurnall. He's parts of it. There's some things that I don't find in him, and I like it. Ohanian's my standby. This is what I had in general relativity, so I just know everything is. It's just like a comfy pillow. And then this is just always he's always insightful, and sometimes he does things more concise than anyone else, and actually right to the point. Okay, so that said, we have a test on Thursday. The does anyone have the study sheet there for you? There's one thing it's just going to be on the mathematics involved with calculating things and whatnot. So I have thus declared that this is correct. Yes, that there. That is, everything is on there that should be. Right. So you're good with that. I will probably not be here till 10:30ish. But what I would do, I will have the test set up in basically one of the rooms for you to start whenever you're ready to go. Okay. I just have somebody unlock the door for you. You guys can start whenever you want. Okay. Take as much time as you want. Come by, ask questions if you have any. If you have another class to go to, just go to the other class and come back. You're on your own, not to things and stuff like that. That makes sense? Questions? Okay, so we're rotating a black hole. We call this a Kerr black hole. Looking at Kerr black holes. Okay, the metric we're going to use is yeah. And again, I would give you this metric. I don't expect you to memorize this metric because I know I can tell if it's right or wrong if I look at one. But if you'd ask me to do it off the top of my head, I can't do this. And I'm not going to have you do something that I don't do myself. So okay, I'm gonna have you do something, but he actually puts it on the user friendly form that I'll have him do. Yeah. Okay, so that's the metric, and so that it takes all the class to just repeat the numbers. So we have that. Now, what did we say A was? Angular momentum per unit mass. That's your angular momentum per unit mass. And we saw last time that if the angle is a 0, you basically recover with the short shield metric. We did that. Now these coordinates here are called, I don't know whether this guy is French or whether he's not French. Makes a difference. I would say the Boyer-Lindquist coordinates, but if he's not French, often the Boyer could be just anglicized and become Boyer. I think he might be French, but I don't know that for a fact. But these coordinates here. R, theta, P, and T coordinates. or Fourier. That's looks like a theta. It should be Fourier. No, Fourier. Lindquist. That's that's the name of the coordinates here. That's usually the standard ones that they're given. I'll say more about them later on. What we want to do, we want to start extracting some information here. Oh, also we did one thing. I haven't had a chance to write up the daily homework assignment on this. You're going to show that the static limit, in other words, t equals not the static limit when t is a constant. So in other words, this term we're going to kill, and then this term will go here. So we're just going to be left with these here. What did we say this is going to be? This would be the flat space-time version of basically an ellipsoid in spheroidal coordinates. And so what you're going to do, you're going to say that ds squared equals dx squared plus dy squared plus dz squared. We looked at what the x, y, and z were on Friday. You're going to take the differential of them. You're going to put them in there, crank out a whole bunch of math, and you're going to recover this expression. Does that make sense? So that's what you're going to do. So in our what we want to start doing is we want to start looking at what does this thing look like. So let's first of all let's look at the case of the infinite redshift. So let's ask where do the infinite redshifts occur? In this metric. So let's think about what we did first of all with the short term metric. So recall, for the short term metric, and how far can I go over here? We had our ds squared equals this. Remember when those days when this got complicated? Remember when you looked at this and oh, it's so hard. Now we have that. See? You're all grown up. Okay. So what do we have? What did we do for the infinite redshift? We found the time variation. What did we do? We said if our clock is stationary. So if our clock is stationary, what happens? DS is 0. No, that's for light. Oh, our ds goes to this d tau squared. If it's stationary, what do you know about dr and d omega? They go up. Right? The constants, so they go out. So this tells me that the d tau squared is this 1 minus s over r d tau squared. We take the square root. And we have this here. And we said the infinite redshift occurs when basically this term here equals 0. So we set GTT equals 0. Right? And what did that give us? That told us that the surface, the infinite redshift, occurs at r equals rs, right? The short radius is 0. Okay. But what do we have in this case? The curved black hole. The curved trick. See. What did we do?
The d theta and d pi is go to 0.
Along with the
dt. dr.
The dr. So hey, and then what does this become?
D tau squared.
That becomes your d tau squared minus sign because of the way we set up the metric. And so what we're going to do is get that the d tau squared equals this guy. So this will give us d tau squared equals this. And what's gonna happen again? Okay, I can write this as the d tau. It's this guy. Again, here's my GTT. So you're gonna have the exact same thing. Those infinite redshift surfaces are gonna occur when this equals 0. So the infinite redshift surface occurs when rho squared equals what? Well, it occurs when the GTT equals 0. That occurs when rho squared is
2GMR.
2GMR. Now, what is rho squared? That's my buddy over here. Okay, so let's notice I deliberately wrote it like this wrong because I didn't want to spoil the surprise. Tell me why this right here is really wrong. I shouldn't say infinite redshift surface. You should say infinite redshift surfaces. It's plural. Because this is a this is a quadratic. Okay. So we actually get now 2 of them. So this is already a new feature that we. So let's actually solve this. Hey, how do we solve that crazy equation? Thank you. Okay, just a quadratic equation. So we're gonna get R equals minus 2GMR. Not that at all. Plus or minus the square root of this quantity squared. Minus 4AC. All over 2A. What we're left. So this R equals 2GM plus or minus. I'll cancel it there. I'll take that 2 inside here, making it a 4, canceling that term there. So this gives me the square root of G squared M squared minus A squared plus N squared. Okay. So there are your 2 surfaces. If you graph them, there's a whole bunch of things you can get here. One is, I gave you from Ohanian, I gave you this picture here. And so what you do is you get this picture here. So the outer part here is going to be the infinite redshift surface here. And then you get an inner one here with this. So if you were to make a graph of this guy. You're going to get this guy here like that. And what happens when theta equals 0 degrees? Sine squared equals 1. So this goes to, if this is 0, goes to 1. Then what happens? Actually, no, when this is 90 degrees, I'm sorry.
Yeah.
This is 90 degrees.
It goes to GM.
It goes to GM here, and then you would end up with these being what?
Did you forget to divide out the two from that first?
Oh, this term, yes, I did.
So it's
Oh, it's your
Zero.
delta?
Okay.
Is that
Yeah, so what you can do is you can if the cosine is equal to 0, if the cosine of this
is the
cosine is equal to cosine of theta is 0, which would be at 90 degrees. What do you get?
either 0 or 2 GM?
Yeah, you get this either 2 GM here or you get a 0 here like this, and you can see that in. Actually, no, you can't really see that in the picture, but it's one of the cases you can actually work out easily here. Normally, this gets a little funky to draw because of the cosine here, but there's 2 cases you can actually draw that relative ease. So you get that one there, and so the other one looks like he just doesn't do anything fancy for it. He just kind of goes like this. So these are the infinite redshifts.
They're the infinite redshift at the singularity.
They're not singularities.
Okay.
They,
So you're past the event horizon then.
they're not event horizons.
I'm not saying aren't you past the event horizon?
No, we haven't done the event horizons yet. So what happens is that the infinite surfaces, the infinite redshift surfaces and the event horizons coincide with the short short black hole. They're not going to coincide here. They're going to be different structure. They're going to be different.
well, data is 90. Then one of the surfaces is at the singularity. Is that
No, it's going to be something different. We're gonna work out the singularity. We haven't worked out the singularity yet. Okay. Questions of that? There's going to be a true singularity at rho equals 0. We'll have to worry about. We have to figure out what that means because it's going to be weird. Questions of that? Okay. Now, what about the event horizons? What am I safety erasing? Thank you. Does everyone have this? I just don't want to touch that. So let's ask where do the event horizons occur? Oh shit, I should have said event horizons. There's one of these 2. I want it to be another surprise. But, oh wow, I'll give it. Okay, so let's figure out where they occur. Since it's a question, I'm going to end this with a question. So let's think about what we do with the short short black hole. The short short. Let's say metric. What do we do? Well, we have this guy here. That there. We look at light. What do you know about ds squared for light?
0.
So 0. So you get the 0. I'm tired of writing it. And I could actually, if I wanted to, I could solve for this DRDT. I know we did it the other way. But I'm going to do it like this because it's going to make it a little bit easier for this guy over here. And if we do that, that gives us this where's it? Well, we'll just write it out. If you do it like that, that gives us this. No. What happens here, we can say that if R equals RS, what is GR dt? This is 0, and that corresponded, remember when we did when we looked at our light cone here like this. We looked at the slope here, like this. And what happened is that this ended up starting to narrow off like this. And so we said when we were at R sub S, that light cone actually went up all the way like that, if this is 0. So we want to do the exact same thing for this over here. Does that make sense? So let's actually go through and do this. So if we do this here, I'm going to set my ds squared to 0. And then it's going to be easiest if I pull out a dt squared. I'm going to I'll set this to 0. I'll take everything to the other side and divide through by dt squared. So I can't get rid of that equation, that's gigantic. Okay, we'll put it up here. So put over here, I'll say set es squared equal to 0 in the curve metric. And solve for dRdt. So if I set this to 0 here, and if I take everything to the other side and divide through by this, actually, no, I'm doing stages. I'll solve for this guy here, and I'll take everything to the other side. So this guy becomes positive. This becomes positive. That's on that side here, so then I have this guy. That became negative. This guy becomes negative. Now what I'm going to do, I'm going to pull a dt squared out of all the terms here, divide through by that, and multiply through by this factor here. I don't want to erase this. Okay, I'm going to write kind of small. Do that. And this is squared. I pulled out this guy here and I've taken it to the other side. And this guy here becomes 1. I'm just going to combine these two roots together. That'll give me a 2 d phi d tau. Because they are the same terms, so I divided, I pulled out a dt squared, leaving a dt in the bottom here.
Oh, side just entered, like, it's just you. You thought that it's not there.
The phi, this and this are the same.
Yeah, no, it's just one of them look very to the side.
Which one?
To the
This guy here?
yeah. I thought it was the side. That's
No,
why I was so confused.
On that turn, didn't you divide the DTs out?
I plot out a DT squared.
Oh, I see.
And so because I'm gonna take that out over here. And so I would have should put in that step, but I just don't have enough space for it. I apologize for that. Right, I don't say I didn't, I'm forced to kind of be jam pack things inside here. Agree? So where do my event horizons occur? How can I make the RD tau equals 0 when don't this is simple, make it simple. All this mess is being multiplied by what?
Delta
Delta
over
over rho squared. So how can I make this whole thing equal to 0?
delta 0.
Delta equals. Okay. So we're gonna delta it right down here. Okay, so if delta equals 0 equals r squared minus 2gmr say squared. What do we have here?
Equidrive.
A quadratic equation. Hey, let's solve this. I really wanted the other one, so. So this is going to be 2gm plus or minus the square root of 4g squared m squared minus 4ac all over 2a, which is 2. And so these guys are going to be what? This is going to become gm plus or minus the square root of g squared m squared minus a squared. Now, okay. I was forced to erase that one term because for infinite redshifts. Let's see if I can squeeze it in. I don't even have to squeeze it in there. Okay. We have two of these here, but what happens at theta equals 0? There is no theta equals 0 there, but what happens if theta equals 0 in the infinite redshift terms? Turn back your notes.
It becomes that.
It becomes this. Okay. So in other words, when your theta equals 0, or theta is 180, these two surfaces touch. So when you draw these, draw these guys. Here's your infinite redshift. Inside there, you're going to get the first one of these guys here. You're going to get this guy that looks like this. Okay, so this right here, this is your event horizon. Okay, so that event horizon is being surrounded by basically this infinite redshift. If you go inside here, this is where it gets hard to draw. Okay. If you go inside here, you're going to basically get these other two ones like this. You're going to get this guy here. You're going to get your infinite redshift here, and then it turns out the other one actually survived. It was on the side here. So you get this message structure like that.
What's the point of having your event horizon?
It's just what the metric has in it. I mean, I don't know. It's not that there's a point in it. It's just.
I mean, yeah, but like the thing I'm trying to say is that once you pass the first one,
You're stuck.
you're stuck.
You're dead.
But like, what happened when you pass the second one?
Well, then I think the physics is wrong because we're going to find out what's going to happen.
Oh.
Okay, I think I'm going to read this. Part of the reason why I brought this book here is I want to read the statement from care on. I think it means that the physics is fundamental. Okay, does that make sense? Now, in the shorts, now what about this true singularity? Okay, so where? Again, I apologize for the thinking, so I wondered here. So where do the true singularities lie? And, okay, so recall for the short short method. Okay, it looked like the rho equals the short radius was basically a singularity. It wasn't. In fact, there was only one singularity in that case. Where did that singularity occur? When little r equals 0. That's where you're getting the infinite curvature. When you're talking about basically these singularities, it's going to be a place basically where you get physical quantities become infinite. And that only occurs if you were to calculate the curvature tensor, which is a scalar, so it's going to be independent of any coordinate system. That'll depend on 1 over the little r. So what happens here is that it occurs at r equals 0. This is where the curvature tensor scalar r, this is a scalar here, basically goes to infinity. Okay, we didn't calculate that, I just said that as a fact. That's what a singularity means. It's basically where you're having these terms actually really going to infinity. Okay. Now, it's not obvious from this. But rho equaling 0 is the singularity for the Kerr metric. In other words, you're getting physical properties that actually look infinity. What might give erase? Yeah, I think I know what I call my black hole picture. Okay. You tell me what it means. Rho equals 0. This is weird. Oh. So you think, oh well, that's easy. Just set rho to 0. What could be the here? Hard. We'll say, well, rho squared was 0. This is my singularity. This is r squared plus a squared plus m squared theta. Done. Okay, you should be a little. What does this mean?
Well, some term goes to infinity, some goes to 0.
Now just on that equation.
R squared equals negative a squared, essentially.
Yeah, so the r squared equals so this appears. Appears to state that r squared equals minus a squared here. Okay. At the singularity when no equals. Tell me why it doesn't mean that.
That's a negative number.
Yeah. Okay. What is your angular momentum here? This is your angular momentum for your mass. Comes in squared. This can only be positive. This term here can only be positive. So this term here is only positive here. So this means that this r squared is negative here. You can't have this r squared be negative. Okay, so you can't have that. Okay, so since A squared is greater than 0. And cosine squared here is greater than 0. R squared would be less than 0, which is not possible. So fix that then. How can I have rho squared equals 0?
Absolute value.
No. It's weird. You're gonna get a very odd result. There's only one way to make it.
Multiply
Two
it,
conditions.
multiply it by 0.
Two things have to be 0.
A and
A can't be 0 because that's your momentum pre mass.
Theta,
Yeah.
you have mass.
Well, the cosine squared of theta must be 0 at the same time that
R
R equals 0. So that's a condition for that to be the case. So this really means, so R equaling 0 really means that R squared is 0 and cosine squared is 0. Okay, can this one over here go? Okay, so I'm just gonna write this figure. So at rho equals 0, cosine square of theta equals 0, and R squared. Okay, well, tell me what this one means.
it's planars
What plane?
like X.
Well, where's my singularity gonna live? It is plane. Well, what plane?
It equals or equals pi over 2.
90 degrees on the XY plane. So this says that the singularity is in the XY plane. Since theta must be pi over 2 root 9 degrees. Now, what does R squared equal 0 mean? And this one's not a fair question to ask because you don't have to remember it, but I can ask it anyways.
It's R is 0.
I agree, but does it mean? Remember how we had those X and Y and Z coordinates on Friday? So recall on Friday. Yeah, we had this X equals the square root A squared, R squared, sine of theta, cosine phi. Y equals the square root of A squared plus R squared, sine of theta, sine of phi, and Z equals R cosine of theta. Okay. What does that mean here? Z is, we want to use a parsing, 0 because we're in the XY plane, so that is 0. Okay, R is?
A cosine.
R is?
0.
Okay, so the R is 0. The sine of 90 is?
1.
Okay, and so what does that give us? So this gives us X equals A cosine phi, Y equals A sine of phi R is Z. Okay, what do these two equations give us?
That's why plane.
Yeah.
Just polar coordinates.
Yeah, what does it get? Upper level physics and engineering majors.
I don't know, triangle.
Oh, I have to leave. I have to have a chat with. Let's go over there and talk to the 5,000 volt source, Jimmy. And then,
Event. This.
yeah, it's a circle, all right? This gives X squared plus Y squared equals A squared. So what is my singularity?
Circling XY plane.
It's just, it's a ring in the XY plane. Of radius of the part of per unit mass. Okay, we have a ring singularity. That's what we have. And so he actually has it as a disk in here, which is actually wrong. Well, he has a disk here. It's actually and my buddy in Vernon has it right. Okay. It's right here. It's actually inside here. Once you go inside the other event horizon, you encounter the ring singularity. Okay. Dun, dun, dun. Ring singularity.
Yeah, the fact that it's not a point makes it weird because like once I mean, not that once you pass, because I mean you're dead by
Oh yeah, you're this is just different ways of being screwed.
but
This is all like that.
let's say you have an indestructible object that go past the singularity, like where it's past the singularity since it's a ring.
It turns out this region here, okay, when you're this will be the definition for tomorrow. Okay, so if we go inside here. So here's our infinite redshift. And here's our first event horizon. This region in here, this is called the ergosphere. That won't kill you. You can actually live, you can survive. Okay. What I want to do next time, because I don't want to start this smell. It's not that it's hard. But I just want to do it. But, yeah. We want to look at what's going to happen inside here, because we're going to get a whole new phenomenon here. It's called frame dragging. What's going to happen is that as this black hole rotates, it's actually going to take the space inside there and actually twist. Yes, I should drag the space along with it. So what's going to happen here is you can't stand still. Now it's not fatal necessarily, but you can't stand still inside here. Once you go past the event horizon, it gets weird. In fact, once you go past the other ones, I'll work out more of the details of this tomorrow, but let me just, I'm not going to be too worried about it because it's not something weird. I think the physics breaks down. This is what Carol says about classes. This is not the interesting. Okay. Where is it? Okay, so this is what he says, and I haven't looked at all the details. We will look at them tomorrow. Not only do we have the usual strangeness of these distinct asymptotic flat regions connected to ours through a black hole. So in other words, get these universes and other stuff. No, don't worry about that yet. But the regions near the ring singularity has additional pathologies. Closed time-like curves. Now, what's a closed time-like curve? How do you make a time machine? Right, here's your here, this is your X. Remember, your world line looks like this. This is your CT. If you made a time machine, what do you have? What would you have to do? Oh, right. You have to come in here. You have to have a world line coming out like this. And then we want to go back to here like this. Right? That's the time machine. That is a closed time-like curve. That's what's going to happen. Okay. What's going to happen is that you're going to come across these. Yeah, so you're going to have these closed time-like curves once you get your ring singularity. It says, okay, so if you consider the trajectories that wind around in phi while keeping theta and t constant. There's this weird thing that has to occur, don't worry about it. Since these paths are closed, they are obviously closed time-like curves. And you can therefore meet yourself in the past with all that entails. Okay, I think that means that the physics is wrong. Okay, I think it means that basically, I would argue that at that point, when you're getting closed time-like curves and you're getting little time machines in here, I think it probably means the physics is wrong. So probably I think this part is probably fine. I think when you're getting in here, you probably need quantum. I think probably the physics is what's fundamentally wrong. That would be my interpretation. Now, that makes for good science fiction. Okay. So what we want to do next time, we want to actually look at what's going to happen inside here, or light. And what we want to do, we want to look at the phi direction out here. So what we're going to do. So this is for tomorrow. So tomorrow. Let's calculate. The phi d tau for light. Okay. In the Earth sphere. Okay. So in other words, we want to be in this region here. And we want to calculate that for light. And what we're going to find out happens is that we're going to get a very, very bizarre property of light in that region. Well, we're going to find out that if we're inside here, let's say the black hole's rotating this way, like this, whether you want to or not, you're going to be circulating that same direction. Okay, even if you take your ship and you try to go in the other direction, you cannot go in the other direction. You can only go in that way because the whole space itself is going to be physically dragged. And so this is actually called frame drag. The actual space itself, as the rotating object, is actually physically pulled. And so you are stuck. You cannot even go that way. In fact, we're going to take light, and light can go this way, making a little circle. Well, let's say light was instead of going that way. It turns out if light's going that way, it turns out light stops. It's just, it has no, it can try to go this way. You're just going to have your light just stopped. It's not going to move.
Oh, silly question. Can you go faster than light then, since your space?
Not in that direction there, because if
Yeah, well, no, not there. But since my space is like being forcefully tried, I'm already having some.
you're still stuck in the light cone.
Oh, okay, well.
Now, what we can do, and what Roger Penrose said, besides something very good first thing, what he realized is that you can actually extract energy from this. So there's something called the Penrose process where you can do something really kind of weird. And you can actually extract energy from your rotating black hole. So in principle, if you had an infinitely sophisticated culture, not culture, scientific, technologically sophisticated culture, you can actually then use one of these to power your society. Don't worry about it. I suspect there are very few that can do this. Unless maybe the 10 ones can. Okay. So that's what we're going to do with those. Okay. Good.